Thank you for the introduction. First of all, I would like to I'm honored to be among the 6 winners, and I would like to thank the NAWARD Foundation, the review committee, and also my wife, my kids for their support, our families, and my colleagues who work with me on this thematic, and my colleagues from the University of Le Havre, Normandy. So I will be talking about hybrid excited synchronous machines, a subject I began to explore more than 2 decades ago during my PhD. So HESM, hybrid excited synchronous machines. So the design of electrical machines is a multidisciplinary activity which requires mastering multi-physics aspects, as highlighted by this slide. We should master the electromagnetism, the mechanical, the thermal. It is also important to consider the applications, and regarding the shift toward the more sustainable societies and the reduction of the use of fossil fuels, there is 2 major applications which are attracting much attention, which is the production of electricity from renewable energies and also the use of electricity in transportation applications. And regarding most of the time contradictory requirements that have to be fulfilled, some scholars consider that the design of electrical machines is both an art and a science. What is hybrid excitation synchronous machines? It's synchronous machines where we combine 2 excitation sources, permanent magnet and wound field excitation. And there is different terminology used to qualify this type of technology: double excitation, hybrid excitation, and combined excitation. This principle allows a wide variety of structures to be realized, and as we can see, we can have 2D structures or 3D structures. And regarding the specificity of those structures, which is the presence of 2 excitation magnetic field sources, there is 2 main criteria: how we combine the two excitation flux sources. So we can have, like here, series hybrid excitation or parallel hybrid excitation machines. They can be 2D or 3D. And also the other specific criteria is the localization. So we can have both sources in the rotor or both sources in the stator or distributed, like here. We have the permanent magnet in the rotor and the excitation winding in the stator. This thematic is a hot spot within the electrical machine designers academic community, and we can see here the number of publications dedicated to this subject, which goes from 1 in 1989 to more than 600 in 2023. And beyond the academic community, the hybrid excited synchronous machines have been used for electrical cars. And in France, we have a small electrical cars called AMI, produced by Citroën, Stellantis Group. And they used a hybrid excited synchronous machine for the traction of this electrical car. And this technology was developed by Valeo. During my PhD, I demonstrated that those machines allow us to bring an additional degree of freedom, whether from a design point of view or a control point of view. And from a design point of view, we defined what we call the hybridization ratio, which highlights the contribution of the permanent magnet excitation as compared to the wound field excitation. And by adjusting this parameter, we can actually shift the higher efficiency area, power efficiency area, towards the area where the machine is most solicited, is most operating. So doing so, we can not only improve the power efficiency, but the energy efficiency and increase the autonomy of electrical vehicles. This has been also demonstrated experimentally, and this is the test bench that we used for that purpose. So the output power is computed by multiplying the torque, measured torque and speed, and the input power include the power converter supplying the armature windings and the excitation windings. So the total efficiency includes the power converters and the machines. And you can see here the drawing of 2 efficiency maps for 2 values of the hybridization ratio. When alpha equal 1, it means that we are using the excitation windings only to weaken the total excitation flux. And when alpha is different from 1, it's lower than 1, it means that we are using the wound field excitation to increase the maximum excitation flux and to weaken it. And by doing so, we can shift the higher power efficiency zone and make it match the most solicited operating area. I also worked on the design of generators, not only motors, and you can see here a flux switching hybrid excited vernier machine. The flux switching principle allows to have all magnetic flux sources located in the stator, armature windings, excitation windings, permanent magnet, and doing so we can have a more efficient cooling and ensure a stability of the performance of the machine. And you can see here the machine under construction. And this one was designed for renewable energy conversion, wind turbines or tidal turbines. I recently led the publication of a book based on my work, mainly my work during my PhD, and it has been published in 2022 by Wiley in English and also in French. There is a French version published by East. I am still working on hybrid excited synchronous machines, and with one of my PhD students, we are working on shifted inductances axis hybrid excited synchronous machines. And you can see here the structure of such a machine. So we have a rotor with wound field excitation, a rotor with permanent magnet, and a variable reluctance rotor. And the idea is to make the rotor shifting according to each other, and the goal is to optimize the operating in the entire torque speed plane. Low speed, high speed, and also partial load operation area. So finally, I hope that I demonstrated and convinced you that hybrid excited synchronous machines allows to bring an additional degree of freedom, whether from a design point of view or a control point of view. And those degrees of freedom allows to address challenges of the design of electrical machines, as for example, the increase of the price of rare earths materials. And also we can imagine from this principle new structures which allows to address different applications, but also regarding the complexity that is brought by this principle, it should be put into perspective with the much more complex IC engine. When you see the number of pieces that we need to build an IC engine, an electrical machine is much more simple. Finally, engineers and researchers have to find solutions in different engineering domains, mainly electrical engineering and mechanical engineering, and this is what we call power mechatronics. Thank you for your attention. Arigatou gozaimasu.